Ooh. Okay, wow. Well, let's cram on with part two. This is a cram, isn't it? A lot of stuff going on. I'm trying to touch on some of the things you might see. Take a look at a little more of a difficult problem. The idea, we're going to use something like a cash register tape on that, and that's what's going to be on this roller. He has a solid cylinder that's going to roll down an incline. It's going to pass over a light, smooth, frictionless pulley, so we don't have to worry about this. But this is a case we're going to need to watch our accelerations. This is a lot like the problems we have where we use pulleys. This has got a little different stuff going on. We've got an inclined plane, and this cylinder has this tape wrapped around it. So as it moves down the incline, it's going to start, if it starts to go this way, and I guess this is a case where we need to really solve for that it's going down. I've got my plus direction is going to be going down, and again we might solve for the acceleration, it's going the other direction. But as this tape goes down, and it's going to roll without slipping, so it's got to roll up as it goes down, roll up some of the tape, and that tape is then going to lift a mass over here up. So part of it, we want to look at this whole system. I've got this mass over here, so I've got these simple pieces. This is a simple piece, or one that we should be familiar with. The tension, I'm going to call up positive. It's going to go up. This is massless, frictionless. All it does is change the direction. The tape then wraps around this pulley, or the cylinder, and it's going to roll down in a plus direction, and we need to figure out what's going on. So we've got both of these things happening. Now, one of the first things we want to do is kind of look at how this motion is going to be the same. Normally, we'd have maybe a block or something here, and it would slide down, and whatever the acceleration this way is, it would be matched by this block going up with the same acceleration. This isn't going to be quite the case here. The idea that the roller is here, it's got to roll, and let's say when it does get down here, it's got to roll, it's going to roll up some of the tape as it goes down. So let's say when it moves from here to here, some distance x, it's got to pull the tape so that this tape gets pulled from here over to here, a distance x. But not only that, it's got to roll, and it's going to roll up some of the tape. So as it moves a distance x, it's got to roll a distance x, and it's going to roll that tape up x. And so the idea that this is going to pull this up, it's going to pull it up really 2x. It's got to pull it up this amount plus this amount, or 2x. And so that is going to be the relationship between the roller and the block. And I expect that the block to be equal to 2 times the acceleration of the roller. So we've done this kind of thing before, and hopefully that has stuck with you. We've got let's kind of do a free body diagram on that. I did a familiar one here on this one with mg and t. When we look at the roller, we've got, of course, gravity's coming down. We have also a normal force, which I don't have on here. It doesn't lead to any motion in this direction, so I'm trying to get rid of some of the clutter there. There's going to be this tension of this tape is going to come up here, and there'll also be a frictional force at the bottom. If it's going to roll without slipping, we need a frictional force to be there. If there was no friction, this would just slip down the incline and wouldn't be forced to roll. I do expect that if this is the plus direction, it's got to roll like this, and so I expect friction will roll it in this direction. Although ultimately when I solve for this, I can get my signs from my equations. So let's take a look at this. If we look at equation 2 of the roller, we've got the forces that are acting, So in terms of this force, I've got mg times the sine of theta. That's pulling this down. That's in the plus direction. Holding it back is going to be the tension in the tape, as well as this frictional force. And that should be equal to the mass times the acceleration of the roller. Okay, but that's part of that. We also have the idea that there's going to be torques. We're going to get this thing to rotate. That sum of the torque should equal I alpha. The torques are going to be the frictional force times R. That's going to want to get it to rotate in the plus direction. I'm calling down positive. And so this force is going to want to rotate it that way. So that's in what I'm going to call the positive direction. So that will be, where am I?
So the A sub r is not a radial acceleration.
Oh, right. Good, thank you. Yeah, I mean A for the roller. Yeah. So the A of the roller is equal to A of the block. Yeah. A lot of times I get thinking in terms of context, and I don't realize that.
It's a translational acceleration.
That's right. So we've got the translational acceleration. The sum of the forces is equal to m times the acceleration of the roller. And then also the torques are getting this thing to rotate. We're going to have the frictional force times r. The moment arm is wanting to rotate it in the plus direction. The tape wants to hold it back, minus t times r. And then that should equal the I times alpha. I is of a disk, 1/2 mr squared. The alpha is a over r. Again, you'll see this thing happening. R cancels with one of these. These two r's we can factor out and cancel with the other r. And so we end up with this equation, friction minus the tension is equal to 1/2 ma radial. So I've got this equation. I've labeled it, I guess, 1 from this guy. This is kind of the simplest one we should be able to do from our previous examples. And we've got this one. It should look reasonably familiar. And now we're adding this idea of the torques. Some of the torques have to equal I alpha. These other ones where the sum of the forces have to equal ma. Okay, so we've got really 1, 2, 3 equations, and we've got how many unknowns? We don't know the tension in the tape. We don't really know the frictional force here that's needed to get that to happen. He just assures us that it doesn't slip, so whatever that frictional force is, whatever is needed to keep that thing going. And so we want to solve these things. Now, probably... let's see. I want to use, well, since I looked at this one, and I want to make sure I don't mess up here. Essentially, these are our equations we want to solve. So I use these 3 equations. Probably what we'll do is take this one, solve for t. This is probably the most natural. Take this t, and then I can put it into these 2 equations, so we can eliminate t. Then I can solve for, once I have that, I could solve for friction between these. Either one of these, probably easiest to do this one. Take this minus t over to the other side is positive, so I would end up adding this t with that. That would be friction. This then can go back up into this equation and solve for that and solve for a radial. So I think that is the final equation with those other things put in. And then we have the radial acceleration. Messy looking expression, but you would take some time to do this for yourself. We look at this. This A could be either positive in the sense that I've got it. That would be true if this is positive. I've got a minus m times g on this side. If this minus sign happens to be big enough, it could turn that negative. So the math will tell me which way this thing is going to roll. Again, I just put the kind of arbitrary direction on this thing as being plus and plus and rolling this way is plus. I do get a positive number, so I think this is kind of an accurate picture. Then we can go back and get the other unknowns. We can get the tension. And let's see, what else would we need? We've already solved for friction. We're eliminating between these two. We could even go back and get what that is if we need it. But primarily, we're looking at the acceleration of the roller. Tricky thing over here, we do know that the acceleration of the block is 2 times the acceleration of the roller. So I've included that here. We've got it also up here, but we put that together. So getting this stuff to all come together, this is kind of tricky. Tricky how we kind of have to set up this free body diagram to really get clear on what's happening. This is a difficult problem, but hopefully you can at least follow along and you should be able to put it together. Whether you can do it on the exam or not, maybe that's not so obvious. But okay, yes?
On the previous slide, where did you get the friction, or the friction times the radius?
Oh, for the torque. Some of the torques would be the friction times R. So R is this way. That wants to get it to rotate in this direction. Wants to rotate like this, and that we would call as positive. That's in the positive direction. So it's going to be the friction times the lever arm, R. Okay, and then of course there's 90 degrees between them, so we just have to say F times R is that. And then same thing with the tension in this cord times that moment arm R is down here. And so that again is tension times R, really times the sine of 90 degrees, which is 1. So probably get comfortable with just being able to do that.
I just saw that the tension and the friction are in the same direction. Essentially, the friction goes the other direction.
Yeah. Right now,
It's rotating, right?
it could go in either direction. When I did the net force on this thing, it's true, tension is in the negative direction as well as the friction is in the negative. So they are in a sense both here trying to hold this thing back. The thing that's driving it forward is mg times the sine of theta. That's that force of force down the incline. The way it's kind of drawn here, this looks like this is too small to overcome these. And I probably should have had a longer looking vector here to overcome those. But they are working against us. Yeah.
But in the torque equation, 2 steps down, the friction becomes positive because it wants to rotate.
Right, good point. Yeah, as far as the direction of the forces, both tension and force are, in terms of forces, are in the negative direction. Yeah, good.
In a linear sense.
Yeah, in a linear sense. And then in the rotational sense, this tension wants to rotate it this way. It wants to actually bring it back up the incline. The friction is wanting to rotate it this way. So this is actually helping us in this rotation, getting this thing to roll instead of just hang on there. So, okay, you're bringing up very good, subtle points that you really kind of got to get your head around. Okay.
I just one last question.
Yeah.
So the angular acceleration there, where you have the sum of the torque is equal to inertia times angular acceleration, line 2. One up from there.
Oh, yeah.
Yeah, so angular acceleration, that's equal to A over R.
Okay, for something like this where it's coming, as it rolls without slipping, the A over R, as you pointed out earlier, that R isn't, is really a tangential R. And this would be true for alpha. AR is equal to R times alpha for if it's not slipping.
And A sub T is equal to R alpha.
A sub T, A tangential?
Yeah, just in general.
Right.
Yeah, okay.
That's right. Yeah.
Is the A sub R equation that you get from the bottom, is that an equation, or was that a substitution?
This one? This is bringing the two together from substituting. These equations, this is equation 1 here, I solve for tension, and I can take this expression into both of these, then take this expression, solve for F, and substitute it in here. So I've brought in T and F, and then I take this and I solve for the acceleration of the roller. And so this is those 3 substitutions, and this is the final product of that. Yeah. Again, yeah, there's lots of steps in between, and I'm relying that your math is good enough that you can take those steps. If you want to just approach it as you would in a math class, say I have 1, 2, 3 equations, I've got 3 unknowns, I can go ahead and solve. And that's what we're doing. So there's lots of ways of doing the math. But I think it's probably easiest, I found it easiest to solve for T, put it into here and here, eliminate T, solve for F, put it into here, and now take this expression and develop my equation. Okay. Okay, again, a nasty one, but it's a good idea to take a look at some of the worst. And if you can understand this, you're doing well. Okay, more rotational stuff. Boy, this is heavy-duty stuff. The idea of angular momentum, we're given L for that. I don't know where that came from, but we use L. And now this is kind of a definition that kind of comes out of the blue, and it's not immediately apparent, you know, who cares? Like, why do we even do this? It is defined as R cross P. So if you've got something with some momentum, the R is going to be the point from some chosen origin, and very often you have the choice. Sometimes there's some natural choices that are better than others, but the idea, and let me illustrate it with something that's moving in a straight line. So this is sort of counterintuitive. The idea that, let's say we're in space here, we've got some mass and it's sliding along, it's going to have some momentum to it, has some velocity, no forces, so it just goes through space in a straight line. So this is what we would say, well, this thing obeys conservation of linear momentum, it just keeps going with the same momentum. The idea of angular momentum, we can apply it to this. And again, this is counterintuitive. It's probably a bad choice of words calling this angular momentum. We do need to, if we're going to apply this, we do need to choose our origin. In this case, I've chosen this point here. As this thing goes through space, it's, you might say if I'm sitting here and I'm looking at this thing go by, it's going to go whizzing by, and it does swing through an angle, so that'll be sort of its claim to angular. But we can go ahead and use this definition to apply it, and again, I need to justify what it is. But let's say we're moving along here, and we pass through here, and let's say I've got some general point out here. The idea of R cross P, that's going to be R times MV times the sine of the angle between them. Okay, so that's the R goes out to where this is located. The P is this way. When we do the cross product, we measure the angle. We really want to put R and P tail to tail. And then this angle, I would call it phi2 for this position. This is the second position, is going to be the same as this. And we can get its magnitude that L2 is going to be R2 times P times the sine of theta 2. The cross product, R cross P, is going to be coming really out of the board at us. We take R and P. If you had done something like this, let's say this is R, the R vector, the P vector. R cross P would be just to indicate that it's coming out of the board. We're not going to need to do too much with direction, since virtually every problem we're going to face is going to be in the plane of the board. But it is, technically, it's going to be pointing out of the board. It wants to go in this direction. one thing we can look at here, this distance r, now as this thing moves, is something that is not immediately apparent, is that the angular momentum of this thing is going to really stay a constant. As it moves off, this r vector gets larger, but this angle will get smaller. And it turns out that when we say r times p times the sine of the angle, let me just rearrange these terms a little bit, p times r times the sine of theta, that r times the sine of this angle will be what we'll call r perpendicular. This r perpendicular is along this line of motion is going to be a distance from our chosen origin out to where this is passing, and this is a perpendicular distance to this line of action. If we look, and this is going to be the simplest place to apply the conservation of angular momentum. The idea that the momentum here, angular momentum, I call it L naught, being this is the one we primarily want to focus on in doing problems, is just going to be P times R perpendicular, but this is going to be the sine of 90 degrees. So that's the angular momentum for this thing traveling in a straight line. We're going to be doing some problems where we need this fact. It's going to be important. But something you should look at is the momentum out here is going to be P times R perpendicular, and that's the same answer we get when we get here. So, and also if we back it up here before this thing even got here, we can come up with the same angular momentum out here. So it's the same everywhere along here. So usually what we'll be doing is getting that angular momentum. The momentum's like this. The angular momentum is coming like this. Is going to have this r perpendicular is going to be the distance from this point that it's moving relative to this line of action. Okay, I think as we do some problems, this will become a little more, hopefully a little more apparent, is the way we'll use this. Now, usually, another form that we use angular momentum a great deal is for a rigid body. And this is something that's going to be a little more intuitive here. The idea that, suppose I've got this steel plate and it's rotating, and it's got some omega, it's got some angular momentum. So it's spinning with some constant value. The angular momentum of the system is really the sum of the individual angular momentums. Here's where you can go back and say, for this piece, the ith piece, there's some r. We're going to be rotating around this point. It's got some momentum that's going to be at right angles to r, because it's going to be all tangential motion as this thing goes into circular motion. So we can apply that. L sub I is going to be r sub I times the momentum times the sine of, well, this was 90 degrees, so that's that. And so that's r sub I, m sub I times v sub I would be the individual angular momentums. If you want to do this in terms of vectors, each one of these is going to be pointing out of the board. And so that's going to tell you the axis of rotation. The axis is like this in the k-hat direction. And again, we're not going to formalize this too much. This gets very powerful when we start to get into 3D problems. But for right now, let's keep it as 2D. This is complicated enough. So we're going to sum these up. Here's where we can say that the velocity of the ith piece, all these velocities are different. The radii are different. So we need to have the radius, the mass, and now the velocity. The velocity, if we put that in, is r sub I times omega. Okay, that was from before, so that's the velocity. Then from these terms, these are r sub I, m sub I of all these pieces are different, but omega, the angular velocity, should all be the same. So I can factor that out, take it out. And then we're left with this term again, m sub I times r sub I squared. We add that up. That is, as we did before, was the moment of inertia. That's I. So I times omega is equal to the angular momentum of this system, or this rigid body that's rotating. Trying to keep all this stuff straight, the angular momentum is analogous to the linear momentum. Again, the moment of inertia is acting like the mass of the object, and the velocity and the angular velocity are comparable. So this can help you kind of keep all this stuff straight, and there's a lot to keep straight. So we can do it in terms of the vector, the angular momentum. If you want to give it a direction, it's off in this direction. Again, we're not going to do too much with that. We will, the time rate of change of the angular momentum, when we take that, we take the derivative with respect to time. The moment of inertia for a rigid body won't change. There could be cases where it starts to change. We're not going to have any of those. We'll have a fixed rigid body. And then we take a d omega dt, but d omega dt is alpha. So the idea is the time rate of change of the angular momentum is equal to the net torque. Okay, that was the net torque is I times alpha, similar to F equals ma, but it's I alpha. And we've got this where the time rate of change of the angular momentum is equal to the net torque. This is comparable to what we did with momentum. dp dt is equal to the net force. So these are some things, and we'll come to this idea of conservation of angular momentum in just a moment. So this is kind of an application of angular momentum to I want to stress also that here we had the idea of something moving in a straight line. We can apply the definition of angular momentum, and so we're going to be doing problems where we have this along with the idea of rigid body rotation when we do a problem, and I'm coming up to a couple. There's a general case, those with like calculus, I think you can follow this. I think I'm going to leave it off. Essentially, it's a general proof. It doesn't have to be rigid bodies. It could be spiral arms in a galaxy. That ultimately, the time rate of change of the angular momentum is going to be equal to the net torque on something. So this is very powerful, but I don't think we need to go down this route here unless somebody's interested in that. Most of the problems you have, like homework problems, they're sort of kind of common sense a bit once you get used to them. The idea that you should maybe look at, I'm just referring to a couple homework problems and won't do them in detail. The idea that if you had some spinning disk and you're going to take another disk and drop it on top, I guess you did this in the lab, right? And this bottom disk is going to start to get this top disk to rotate, and after after the skidding, at first when it drops on there, they're not moving together, so they kind of skid on one another. But this one's motion gets the top one moving, and eventually they come to relative rest with one another, but still rotating with some angular velocity. I think I'll just point to that and just kind of point this out. The idea that angular momentum is conserved if the net torques are zero. By net torques is when we drop this on, there's going to be equal and opposite torques on these. So overall, the angular momentum will be conserved, and so that's where we can use this from the before picture to the after picture. Another one you maybe want to look at is a disk going around here, the circle. We can apply a pull on this. We can apply a force that's going to pull in this direction. But now the force is going to be pulling this direction. The R goes this way. They're going to be 180 degrees out of phase, or out of angle with respect to one another. And so the net torque is really zero. This pulling in on this doesn't per se directly get this thing to speed up. However, as we pull in on this thing, the angular momentum will be conserved. By the net torque, excuse me, I'm misspeaking here. The net torque due to this force times R is going to be 0 because they're 180 degrees to one another. Since the net torque is 0, the angular momentum will be conserved. And so we're take advantage of that. These are relatively simple problems, but definitely take a look at them and make sure you're comfortable with those. Okay, here's some problems that he's been doing a number of these for over the years, and I expect that it's not going to stop. This is a problem. We've got a clay ball and a stick. Is it a meter stick? Yeah, it's a meter stick. The meter stick is traveling up. This clay ball is traveling over to the right, and they're going to collide, and the clay ball is going to stick to the meter stick. So it's traveling this way, and then the whole system is going to start to rotate, and it's also going to take off. Now, there's a lot going on here, and we're going to break it down into linear motion and rotational motion. So let's say we've got the clay ball, 0.5 kilograms of clay is traveling 3 meters per second this way and has a collision with a 0.25 kilogram meter stick traveling 4 meters per second perpendicular, and the collision is perfectly inelastic, so the clay sticks, and the meter stick at one end, and he's asking, what are the linear speed, the angular speed, and the direction of travel after the collision? So there's a number of things we need to do. The first part, as far as the linear speed, when these two collide, there's going to be forces between these two, but they're going to be what we call internal to the system, so that there's no external forces. Since there's no external forces, the linear momentum should be conserved. So what we'll do is play with the momentum in the initial momentum. We have the clay ball traveling 0.5 times 3 meters per second, and that's going to be in the I direction. The meter stick is coming straight up and is going to skewer this thing at 0.25 times 4 meters per second. That's in the J hat direction. So this is the initial momentum. Okay, now the final momentum is going to be these two things stuck together. The 0.5 and the 0.25 is going to be a 0.75, the clay ball and the meter stick collectively. Times the final velocity. There's going to be something in the I hat direction as well as in the J hat direction. Keep in mind that the overall momentum of this thing is going up off the screen at an angle up this direction. I'm going to be playing with that coming in here. They're going to skewer, and the center of mass of the system, that's what's going to move in a straight line, and I do expect that it's going to travel up in this direction. It's getting its motion this way as well as this way, and so it's going to take off that way. And that would be the center of mass. So if you think of this clay ball stuck on the end, this center of mass is going to be some point here, and we're going to need to find that. And we'll find that, and then also what's going to take place is these internal forces are 0. There's no external torques, and therefore angular momentum will be conserved. And so there's going to be 2 points of motion. One is the center of mass is going to go up in a straight line, but it's also going to start to rotate around the center of mass. And so we've got both of these motions happening. Okay, so let's break this down. Linear momentum is again, the relatively easy. We've got the clay ball, we've got the meter stick coming in, that's the initial momentum. We need to, initial momentum. This is the final momentum. I don't know what the velocity is. I'm not sure what the angle is. It's going to go off at some angle. We need to find that direction, that angle. That's going to be from the final. We can set P initial equal to P final. And here I've got some actual numbers here. I can get P initial equal to P final. And maybe I'll let you work through that detail. But you get V final, so you get an actual speed. Consider we've got these two equations. We've got two unknowns. We've got the x term. We're going to take this in the x direction, set it equal to 1.5. We're going to take this other term in the j direction, set it equal to here. And so we've got two equations, the x equation and the y equation. And we can solve for the final velocity as well as the angle that it's going up. So it's headed up at a 33.7, and it's got a final velocity of 2.4 going off in that direction. So that's linear momentum, tells us that motion. Now the more difficult one is going to be this idea that the moment of inertia, and we've got to kind of breaks, think of this as like a puzzle, we got to start to lay it out here. We're going to need to find where that center of mass is, so we need to do a center of mass problem. We talked about center of mass a little earlier. Now we're going to actually apply that definition to get the y center of mass. Also, we're going to, this whole thing is going to be rotating around the center of mass. So that's going to lead to the idea of rotational inertia. In order to do that, we're going to need to get the rotational inertia of the meter stick and the clay ball. Okay, so let's consider that, well, okay, I want to come back to here. Let me do this first. And then we're going to take these two things together and deal with angular momentum, setting the initial equal to the final and finding what that final angular velocity is. So there's a lot more pieces we need to put together. So we need to get the center of mass. And the first thing you want to do when you're going to find, we want to find where that is, because that's going to be that rotation around that point. So the y center of mass, I need to measure from some point. I chose the middle of the meter stick. You don't have to. You could choose the ends. You can choose any point. You can choose a point out here. It's not going to be convenient. This is relatively convenient here, since this would be at the very center of the meter stick. Its position for its center of mass is going to be 0. So let me do the center of mass of this thing. It should be the sum of the individual masses times their, in this case it's going to be their y value, since we're going up here. And we're going to add these together. So this is going to be your clay ball. It's going to sit out here at a distance of a ½ meter away. So that'll be the mass of the clay ball times its position, plus the meter stick, 0.25 kilograms, but its center of mass is going to be at my chosen origin, so that's going to be 0. It's going to simplify my math a little bit. And then I'm going to divide by the total mass, which is going to be the clay ball plus the meter stick. We've got that. And this 0 kind of helps here, and I can solve for the y center of mass, 0.33, or about 1/3 of a meter. That is measured up from the origin. So that is a measurement from the center of the stick. Okay, now the thing is, we've got this clay ball is going to be traveling on a straight line. We've talked about how an object in moving in a straight line has its angular momentum is conserved. Now, ultimately, what we want to get to is that rotation is going to take place at the center of mass, and so we want to do everything relative to that chosen pivot point at the center of mass. So if I take 3 meters per second times that r perpendicular, that would give me the angular momentum of the clay ball initially, It's coming in this way. The meter stick is not turned yet. But as it comes in, it's going to make contact. And this is where I want to draw my R perpendicular. And so I can get that from the math. Once I know that this is a third of a meter, this is going to be a sixth of a meter, or 0.1667 would be that perpendicular distance. And that's what I'm going to want to use when I'll come back to this, but I'm going to use that with the clay ball. The eye of the system, we need to be able to come up ultimately with the eye of the system to do the conservation of angular momentum. These two things are going to get stuck together. When they get stuck together, they're going to start to rotate. So let's get the moment of inertia for that. It is going to rotate around the combined center of mass. So one of the first things we have to do is get the meter stick itself. The meter stick for around the center of mass is 1/12 mr squared, and plus the mass times d squared. D is the distance to the center of mass of the meter stick. So this distance we already found here was a third of a meter down. So we use that for the moment of inertia. Then we also add the moment of inertia of the clay ball, which is going to be spinning around this thing. That's going to be that mass times the R perpendicular, that perpendicular distance, which again is a sixth of a meter. And then the sum of those two is going to give us the moment of inertia of this system. So we've got the moment of inertia of this thing about the center of mass. Okay, whew. Okay, not easy stuff. So again, I need to know where the center of mass is. So I know which point it's going to rotate around. I need to get the moment of inertia around that point as it spins. And now we can address the angular momentum. Initially, we had the clay ball coming in here at 3 meters per second. So it's coming in here, it's going to go through this perpendicular distance, a sixth of a meter, the difference between these two. It's coming in at 90 degrees to that. We have the meter stick traveling at 4 meters per second. It's got a distance of 0.33 up to here. However, the angle that it's coming in at, R times that is going to be 0. There's a little easier way to see this. This, through the center of mass, if this meter stick is passing right through, it has no radius, and that radius is 0. So there's going to be no contribution initially to this meter stick. It's going to come straight up and skewer this clay ball, but it's doing nothing with this motion to set this thing rotating. So hopefully this makes some sense kind of intuitively. The clay ball coming in here is going to come in here and give this a kick this way, start to rotate it. The meter stick really doesn't contribute. It's coming in at a velocity that is anti-parallel to the radius, and the angle of that is going to be 0. So we just have this for the clay ball. Then we want to say that L initial is equal to L final. Now we have a case where we want to use for angular momentum, we want to use the eye of the system along with the final angular velocity, which is what we're looking for. So I can set that initial angular momentum equal to the final angular momentum. I know what I is for the system. I just need to solve for omega final. So at this point, now the math becomes trivial, and we can solve for the angular velocity of this thing. So, whew. Okay, this is a lot to swallow here. We've got we do have a lot going on. We've got rigid body rotation. We have the motion of a mass along a straight line having angular momentum. It's going to it wants to kick this thing and start it rotating. So it's important. From linear momentum, we got the direction that the center of mass travels, and then around that center of mass, this thing is going to be rotating with this angular velocity.
Can I ask a question?
Yeah.
Suppose there was a peg or a nail going through the origin there, and it was on a flat surface, a flat plane, not so gravity really would.
Okay, yeah. We want to cut out external forces.
Would that nail be an external force?
Yeah. Okay, in fact, I anticipated that. Good, your thinking is right on.
We couldn't use conservation of momentum.
Right. In fact, yeah, so this is a slightly different problem. This is one, as John was saying, is pegged here. We put a nail or something here. And the idea is that there can be external forces from that nail onto this rod. And so we say there can be external forces. So linear momentum will not hold. However, angular momentum will hold, because if this is a frictionless axle, it can't apply any torques to this thing. It just can spin freely around that axis, and that's what's going to happen. So let me look at this. We've got a ball that's going to hit at 45 degrees. This rod is going to just sit there, and as John says, we don't have gravity, no other external forces. We could be maybe looking down at this. It could be on a tabletop, and this could be like a ball or a puck that hits it and comes off. And then what's going to happen is going to start to get this thing to rotate around this point. So the part about linear momentum doesn't hold. However, there are no external torques, and so angular momentum holds. And I think this is actually a little easier to see, but let's kind of look at the wording here. We've got a 0.5 kilogram ball that hits the rod at its center at an angle of 45 degrees coming in. The initial speed of the ball is 10 meters per second, and after the ball bounces, also at 45 degrees, off the rod, its speed is 5 meters per second. So it's going to come in and bounce off, but it's going to lose some of its speed. It's going to give up some of its energy that's going to boot this thing and cause this thing to rotate. Okay, initial speed of the ball is 10 meters per second. After it bounces is 5 meters per second. The rod is free to rotate about its end point. Okay, if the rod has a mass of 2 kilograms and a length of 2.5 meters, he wants to know, well, how much heat is created in the collision. So he's asking for energy, but we've got to do all this other stuff before we can even answer his question. So let's look at it from the point of view of angular momentum. Ultimately, we're going to rotate around this point, and so we want to get the angular momentum around that point. So initially, that rod is at rest, but the ball is coming in here at 10 meters per second. It's going to strike the middle, and then it's going to bounce off. We want to since there's no external torques, we can use the idea of conservation of angular momentum. So my initial angular momentum is just this clay ball. It's coming in. What I would like to do, it's coming in along, I'm calling this the line of action, and it's easiest to let this thing come through times this perpendicular distance. So it's got its momentum, mv, along this line. This is the perpendicular distance, so the angular momentum is just that momentum times that distance, that perpendicular distance. And if you look at what we've got here, we've got the mass of the ball, its speed, times our perpendicular. I want to come up with that. That's going to be half the length of the stick, and this was a 45-degree angle, so times the sine of half the stick times the sine of 45 is our perpendicular. The rod is not rotating, and so we have an angular momentum that's 0.22. And I'm calling this direction, I'm calling this positive. So in a sense, it's coming along. In a sense, it wants to rotate this way. So I'm calling this positive rotation. If you're bothered by that, it's okay. Go ahead and stick a minus sign in front of it. But whatever sense you have, just go ahead and stick with it. So I'm just going to call that plus if you're going to follow these signs that I'm using. And then it's going to go off here, and then the stick is also going to be rotating. So the final angular momentum is got two parts to it. Is this ball that's going off times, that's going to be its momentum, times this r perpendicular. It wants to get and rotate it the other direction. I'm calling it negative. A lot of you would like to call that positive, and that's okay. The signs, when we set the two things equal, the signs can be either direction. And just stay consistent. So L final is the mass of the ball. It's now traveling at 5 meters per second. It's still got the same r perpendicular there. And then, but now we also have the stick here that's rotating around the end, and that was a 1/3 mr squared for the moment of inertia of the rod, and we can crunch the numbers here, and there's going to be an omega. And so the idea of the final angular momentum is equal to, this should be an equal sign, is equal to the initial angular momentum. We go ahead and set these two things equal, so I have that, and set it equal to this, and we can solve for omega final. We've just got the one term here. This has just got the number, so when we go ahead and set that equal, we can solve for omega final. I get 3.18 radians per second for omega final. So that is telling us, how fast this thing is now rotating. The ball continues to go off, and so he wants to know, though, how much heat was created in the collision. So we want to see what happened to our energy. So I look at my initial energy. That is just the kinetic energy of this ball coming in here, 0.5, 1/2 mv squared, and I see that that's 25 joules. Is that initial energy?
All that is just given.
Yeah, this would be given. Yeah, yeah. Okay. So yeah, I'm just using these numbers here. 1/2 mr v squared has to be equal to, and then crunching these numbers, 25 joules. Then I want to get the final energy. Well, I've got two things happening. I've got the clay ball is now traveling at 5 meters per second, so 1/2 mv squared. So I use my standard energy for that. Now,
Going in a negative.
As far as the direction with the v squared, it really doesn't matter. With energy, we're going to deal with strictly positive terms for kinetic energy. It'll always be positive. That's a nice thing about energy. You don't have to worry about such things. Then we have this rod that's rotating with this angular velocity. So I want to use 1/2 the I times omega squared. Okay, similar to, this is 1/2 mv squared. This is 1/2 I omega squared. I'm having trouble myself here saying all this. We've got omega, we can stick that in, we have the mass, and so this is 1/2 I omega squared, kind of keeping these two terms straight. Again, I'm kind of mixing energy. It's more convenient to go 1/2 mv squared for the ball and for the rod, and the combination together, that would be better expressed this way. So either way is really giving us the kinetic energy. Sticking in the numbers, we now have 11.5 joules compared to 25. So we have lost some energy. We're going to go, the initial is 25 joules minus this energy, and that gives us, with the energy that we've lost, that's the heat. I don't like my signs here. This is going to be a positive quantity. This is going to be the difference between these two.
Does that mean heat is gained?
Oh, well, it's lost, and I'm not expressing this well. The initial energy was 25 joules, and the final energy is 11.5. So clearly we lost some energy. Where did it go? Heat, we call it a positive term, and I got a little clumsy here.
The sentence says created.
Yeah, and that would be created in the collision. Yeah.
The idea of positive.
Right. Heat is something we call positive. I've gotten a bit sloppy here. I guess I would have gone heat. No, this is right. If I want to get heat, usually we'll say that E initial is equal to E, the energy final, plus any heat that's generated. I want to solve for that heat. Heat is going to be a positive quantity. It's tied up in the kinetic energy, the molecules that are inside this thing. This is what heat is. And so this is just like kinetic energy is going to always be positive. This heat is going to be positive. So.
Are these slides up online?
Yeah, Dr. Young sent you a link so you can go through them. And I know a lot of these are small, kind of difficult to read. But you can pick through those. It's a PDF file that has all the slides. So you can take a look at that. Yeah.
And the moment of inertia of a rod is a value that will be given to us, right?
Right. Now, he could give you just the rod about the center. He could say the moment of inertia of a rod is 1/12 ml squared. And he's got a table, and virtually anything he gives you is likely to have the moment of inertia about the center of mass. But in a lot of problems, you're going to want to go an axis like this one off the center. And so you can use the parallel axis theorem to get at what that is. And we had done that earlier, how to get using the parallel axis theorem, how to get that for a stick around the end.
So you didn't calculate that here?
I didn't calculate that here. I took it as a known. I did it earlier in the review, but yeah, that's a good point. He could not give you that. The book in chapter 10, they give you the rod both about the center and about the end. And yeah.
The negative right in front of the final momentum up there.
Oh, yeah. Okay. Thanks for bringing that up. Yeah. What about the signs? The final momentum is going to be the clay ball traveling in this direction. The meter stick's going to go this way. So the clay ball is coming this way. There's a tendency, if you kind of look at it, there's a rotation around this point as it moves this way. It wants to rotate it this way, which I was calling negative and calling this other direction positive. So I do have the clay ball is going off. It wants to rotate this way. I'm calling this negative. The other direction I'm calling positive. That's going to be the 1/3 mr squared. That would be the I of the rod times the angular velocity. So that goes in as positive. The rod is going to be rotating like this, calling this positive. Again, the clay ball coming in here around this point tends to want to circulate this way. Coming out this way, it wants to circulate the other direction. The rod, as it gets moving, is going to want to rotate in this direction. And that's the direction I was calling as positive. Okay?
It just seems like that stick should be negative rotation.
Well, you would agree that it would be booted this direction.
I always think of the clockwise.
Yeah, and I apologize for that, or somewhat apologize. I think people the students that I've worked with have been following that, which is usually the kind of the standard sign convention. That anything like in a math class that is rotating in the positive direction, it's going to be counterclockwise. Negative is counterclockwise. Now, you can do it either direction. It's similar to calling your x-axis. You can say it's plus that way.
Did you get a different number though?
You won't get a different number, other than possibly the signs could be the opposite. But essentially, I'm just making that choice. And we used to do that more, and I think the students that are kind of picking up and using the kind of standard convention that we call.
Counterclockwise is positive, clockwise is negative.
Right, yeah. And that's how you'd probably be exposed to it, like in a math class. But you could imagine also, however you do that, you could go on the other side of the board and look at the same problem, and you got everything reversed. So it's really no different than saying I'm going to call this, my minus y direction compared to that. It's very similar. Yeah. Okay, wow. Nasty. Well, let's do one. I'm not going to do this one. I think it's worth talking about this one. How are you doing? This is brutal, I know. Okay, he's going to make a rigid square made out of 4 long rods. So he's just going to attach these like this. There's nothing in here, so it's not like a solid box. All it is these sticks glued together at the corners. They're pinned here at this axis A, so it's going to rotate with that. And he gives you the various dimensions. Okay, he also says this clay is going to be just small enough that it's not going to appreciably change the center of mass of this little system. It wouldn't be a big deal to include it, but it's kind of nasty enough without that. One of the things, this thing is going to rotate around this point A, and we got these 4 sticks here. They're going to rotate. We're going to need to know the moment of inertia, so let's kind of get that, and that's about point A. We can go ahead and do that. We've got these 4 sticks. 2 of them, this one and this one, is going to be, where am I here? We're going to say I about point A is going to be 2, and these 1/3 ml squareds would be these 2 rods. We've got 2 of them, so we just take times 2. We're just adding them all up. And then we have these other 2 rods, this rod and this rod, which they're going to rotate around this point. So we really need the parallel axis theorem to have them rotate not around their center, but about this point. So to use the parallel axis theorem, we're going to need to know this distance from the axle to the center of mass of the stick. And so from these individual parts here, excuse me, I've got the distance D that's this distance from the center. We're going to need that. This is going to be L over 2 squared plus L squared, just so Pythagorean theorem, is equal to D squared. And you can come up with that in relation to the length of that stick. Then we're going to add these up. So again, the moment of inertia around point A is 2 of these sticks that are rotating around the end, plus 2 of them that are going to be, this is going to be here we're going to use for the parallel axis 1/12 ml squared plus md squared, where d is this distance. So again, parallel axis. I've got that here, and we can go ahead and put that together with this, doing some math and basically just sticking in those numbers, and we're going to come up with the moment of inertia of this thing as it rotates around this point. So we need to set that aside. We're going to need that. Okay, the main guts of the problem are this. We're going to send this little clay ball in with some velocity. We need to find out what that velocity is. It's going to come in, it's going to stick onto the corner of this apparatus, and it's going to give it a little nudge, and it's going to be a case of conservation of momentum, since it's free to rotate around this point. Conservation, excuse me, not of momentum, but of angular momentum. This is coming in along this line. Its R perpendicular is going to be the length of one of these sticks. Okay, it's coming along this axis. It's going to rotate around this point, so this again is R perpendicular coming in. And then the idea is we're going to set the wind with this collision, where it comes in and gives it a boot, is going to tend to get this thing to start to rotate. And this thing could rotate till it's vertical, or at least a diagonal is vertical. And the idea, we would need to get enough velocity, that it had enough angular velocity that it would go up, and if it could just stand up here, up at this point, and have the kinetic energy 0, then the rest of the way it would then fall the rest of the way and make it over. So he wants to know what this velocity is so that this is just enough to knock this thing up and over onto its side. Okay, this first part is the idea of conservation of angular momentum. We have just this mass coming in times r perpendicular, so that is that. The velocity we don't know yet, we'll come back to that, but we do know that 0.3 meters is this r perpendicular. That's got to equal the final, which would be this thing rotating. And again, he just told you to kind of ignore the clay ball at this point. We need it here to give us this boost, but we have the moment of inertia times omega, and we need to solve, of course, for this velocity, but we don't know omega either. So we're going to end up working backwards. So let's just leave these as symbols and pretend we know. Then the idea is once this thing gets set with some initial angular velocity, it's got some initial angular momentum, it's going to come up. Now, as it rises, gravity is doing work, so we want to be careful. We do have the idea of conservation of energy. So again, this collision is conservation of angular momentum, and then this motion here is up to the top is going to be conservation of energy. So whatever that omega is, I know that 1/2 I omega squared is the initial energy of this thing just as it's starting to come up. It hasn't appreciably come off of the table yet. It's still got that omega. And then it's going to go up, and it should raise its center of mass from here on up a little bit, and then its kinetic energy would be 0, and then it's going to fall the rest of the way. So we want to get enough here to get it upright. So again, yes?
How do we calculate that h, the 0.06 meters?
Oh, yeah, okay, the h, yeah, I've got some details up here. It is, if I get, this is half the length of that, obviously, that's half the length. And then if I can get that diagonal, it looks like that's what I've done, h, L over 2 times the cosine of 45 minus L over 2 should be that h.
So h is half, like?
It's going to be the diameter. So this total distance across here, half the diameter of this thing is going to be L over 2 squared plus L over 2 squared, and then square root, just Pythagorean theorem would give us this. And then we're going to subtract the original half of that length from that, and then the leftovers is the h that this thing is going to go up. So the center of mass just goes up a little bit. Now I'm confusing myself as far as looking at this. L over 2 times the cosine of what's that? Multiply.
Just divide the cosine 45.
Okay. Yeah, if you talk this L over 2 and cosine 45, L over 2 cosine 45 would over cosine 45. Yeah, I'm confusing myself what I'm doing here.
Where's the 45? Which side is it?
Yeah, good question.
Does it matter which side it's on?
Well, of course, all of these angles are going to be 45s.
Which one are referencing?
Yeah, and I'm not, now I'm looking at my work and I'm kind of saying, what did I do? Maybe let's try this, set this aside for a second. The idea that this is L, L times the cosine of 45 would be this height. Oh, yeah, L cosine 45 would be this. I think this is what the student was saying here. That's going to be this. So this is L times the cosine of 45. And then we subtract L over 2.
The angle 45 would be at the bottom.
Yeah. I think, let's see, I
How are you
messed.
subtracting over 2?
Oh, we want to get the amount that goes up from this. This is going to be L over 2. So this is the actual center of mass where we started. And then as we tip it up, it's going to go from this line up to here. So I want to get that little bit of distance.
Yeah.
And I think it works out okay. This would be L cosine 45 would be this height minus L over 2. So as I'm looking at this, I think I want just L cosine 45. I don't want this 2 in there. So right now I'm not sure about the problem. I'm not sure that this is the right answer. I need to crunch. In fact, I'm very suspicious of it now.
It really seems like it should just be L cosine.
Yes, I agree. I think basically put your x through that. That should be, yeah, L cosine of 45 would be this whole height minus L over 2. So so no 2 there. And that will change things. This is going to be, I've got to get rid of this 2 on this one. Yeah.
45 would be the total diagonal.
Right, yeah.
So the center of mass.
L,
L cosine.
well, if this is L,
Yeah.
cosine 45, that should be,
Wouldn't it give you all the way up to the top? No, it would go past the center.
I think it should just go just to the center, and I think that's what I want. I want L cosine of that. That would drop it back to there. So this right triangle here, this is L, this 45, and then we've got that height. So I screwed up. Don't let that happen to you.
So going all the way to the top would be 2 times L cosine of 45.
Right. Okay, I'm sorry for the confusion. It happens to us all, and I haven't seen this. So be suspicious of this number. I'm sure it's not right. And so you're going to go ahead and use that idea of conservation of energy. Let's kind of get back to the big picture here. Is going to be this initial energy that it had, rotational energy, coming up to the top where the kinetic energy is 0, and we just have the potential energy, the mg, and that h, which is not right, should be here. And then we can go ahead and we need to solve this for omega. This would be, and then kind of work backwards. Once I have omega, I can then go back to here, substitute that in, and then I can go back here and get that velocity. And this is what he's asking. What is the minimum velocity for this clay ball going to hit this thing to dump this thing over onto its side? So the basic strategy is there. Whew, okay, I know we're running long. This is definitely the nastiest stuff. I think I'm going to set this one aside. Anybody wants to see it? Let's talk about statics for a moment. You're bound to get a statics problem. And after all we've been through, this is actually the easy stuff, which is probably a good little reprieve before moving on to the exam. The idea that if it's static, if there's no motion, that means that the sum of all the forces, both the x, y, and the z, have to add up to 0. And also the torques around any point you choose is going to be 0. Basically, this object doesn't translate. It also doesn't rotate. So the physics we can explain in that real quick line. But now doing this, I want to come back to doing statics problems. We need to be able to deal with torques. And I want to talk about this because calculating torques, I talked about this earlier, that we apply a net force F perpendicular times this R is the most intuitive way of thinking of the torques. If we kick in an additional angle, this is more general, RF times the sine of the angle. But then we can rearrange terms. With this we can go F times R sine theta, and that is what we'll call R times the sine of theta is going to be this perpendicular distance. We use this kind of reasoning a lot with these problems. How far are we from that line of action? So if you've got this force, you can, and see, it could be up here, but you can slide that force anywhere along its line of action. This is not intuitive, but I apply that force times that perpendicular distance to that line of action will give me the torque. So we've really got three ways of calculating torque, and they're really saying the same thing. In problems we can mix and match these. This again is the most intuitive. R times F perpendicular. R times F times the sine of theta is good and most general. And then this one is going to be employed a great deal in problems, is that the torque is just going to be F times R perpendicular. You just take that force, slide it along its line of action, and apply it at a point that is perpendicular to your point of rotation, and then immediately you can calculate your torques. So let me show you this in action. This is in the next one. Let me show you this. Let's start off with just kind of a little basic one. That we have this beam up here. We've got a sign that's hanging on it, and it gives us the width, 2L. The horizontal beam is hinged at the wall, supported by this cable. Determine the tension in the cable and the components of the reaction force exerted by the wall on the beam in terms of our variables. There are no numbers here, just the width of this thing. W is weight. That's the weight of the sign. In terms of D, the distance over to the sign. L, this is, well, actually 2L is kind of the width of the sign. And then the angle that the support wire is holding, this is angle theta. So this is kind of the force diagram that's on that. We're going to have a pin here that can apply forces. So it is free to rotate around this point. But these two forces at that pin are not going to contribute any kind of torque to this. So choosing this point is a good one to use as a reference point. The weight is going to want to get this thing to rotate this direction, and the tension wants to get it to rotate counterclockwise. Now, what did I do as far as torque? I think I'm... Well, let's look at this first. The forces are the easiest to kind of look at. We've got the force in the x, and then the tension has a component in this direction. I'm calling f of x in the positive direction. This is in the negative direction, so I've got the force in the x. It's going to depend on the tension, so I can't really get out what that is yet, even though that's what he's going to be looking for. And then the forces in the y direction is going to be this force. We're going to have the tension has a component that's up, t sine theta, and w is down. That, and so we've got the force in the y is a function of these things, but wait a minute, I'm burning out here fast, but let me. Most of these problems, we have the force equations, we also have the torque equations. Usually the torque equation is why it's here, this is kind of the critical piece that we need for statics. Let's look at the torques around this thing. We've got W times D plus L, so I'm calling this direction, I'm doing it again on you, that this direction I'm calling positive. This tension wants to get it to rotate the other direction. I'm calling that negative, just t times the sine of theta times this distance, d plus 2r. You'll notice you're wondering, well, does it matter what direction I call positive? If you just come through this thing, since it's equal to 0, multiply it through by a negative, this makes this positive, this would make that negative. So if you want to stick to the idea that anything rotating this way is negative and the other way positive, a simple sign change there is okay. So it really doesn't matter how you want to do that. And we are using these several forms here. We've got the R out here, so it's D plus 2L all the way out here for the tension, times the tension, times the sine is the vertical. That's, again, want to rotate it that way, or I'm calling that in the negative direction. And the weight of the sine times this distance. Okay, that would be D plus L, and that would be the lever arm for the weight. So from this we can get what the tension is. Once I have the tension, I can actually go back. I need the tension in both the X and the Y. So once I determine that, I can then go through and get the forces in the X and the forces in the Y. Okay, I'm kind of bumbling here. I'm starting to come apart here. But anyway, this is... it would be an example problem that you could do. This is a past exam question. He's gotten nastier. This is a homework problem. Okay, this is one more, I promise. But I want to show you, but it has some very powerful things going on how to do it. In the solutions manual, if you look for this problem, they immediately break things up. And the problem is we've got a bunch of unknowns. We've got the weight of the painter is going to be standing on this ladder. It gives us the mass, so we've got her weight, 70 kilograms. And then we need to find what the forces are at the bottom. This is holding, these are the normal forces from the floor on that. They also want to know the tension in this little cable or support across here. And then these two pieces are put together as a pin, as a kind of a hinge. Now what you can do, the problem is I've got 1, 2, 3, 4, 5 unknowns. So this means that, wow, mathematically this is probably going to get nasty. Although a lot of you with calculators doing linear algebra have no trouble with that. But what can be very helpful in this strategizing this thing is before you take it apart and blow it apart and say that these are all in equilibrium, the overall ladder is in equilibrium. So when I keep it whole, these tensions that are inside, they're equal and opposite. They tend to cancel out. Also, these support forces up here, action and reaction, you'll notice how these are different. Whatever force is on this one, action, reaction is on this one. This force is up, this is force is down, or maybe they're the other way, but they will always be equal and opposite. But we can ignore those. Those are, because they're action, reaction, they're internal forces. And I can do the ladder problem getting as much information as I can by keeping it whole. So I can get at what these normal forces are by doing this problem. And what I'm going to do is take the torques around. It's best to use a point that has the most number of unknowns. I got an unknown here and an unknown here. Could do it either one. This one I'll choose this point. The weight of the painter is coming down. Now what I'm going to do is I want to get the torques around point A. A itself, normal at A, is going to be 0 because of there's no there's no R to it, so it's right at the point. It's not going to lead to rotation. But if you imagine this pinned and this whole thing could rotate, she's stepping on it is going to want to rotate it this direction, and the normal force at B is going to want to rotate it the other direction. So the two torques should cancel out. So if I look at this, n sub b times this whole distance, which was 2 meters. And I'm calling that positive, so this you're probably a little more comfortable with. It's going to rotate in the plus direction. And then the painter is going to be here. It wants to rotate it in the other direction. Now, as far as seeing this, we could calculate these angles and this distance. Basically, this is 4 meters here. She's 3 meters up to the top of the ladder. So she's really 3/4 the way up, and also 3/4 the way over. If you look at her line of action, if you bring that force and slide it down here, if you can see this, it's going to help. You take that force times that distance. This was 2 meters, halfway is 1 meter. This is going to be 3/4 of a meter. So I can calculate that torque relatively easy. That's a minus 3/4 of a meter times W. Wants to rotate the other way. And then we can get n sub b, the normal force at this point. Then we can go back to the forces in the y. The two upward normal forces minus the weight have to equal 0. And so I can get the normal force at A. So immediately I get 2. So I'm going to go from 5 unknowns now just down to 3 unknowns. These two are given. Now the idea is, if I want to get at these other forces, like up here and this cross piece, I can take this apart. Everything is in equilibrium. Both sides of this thing are going to be in equilibrium. In fact, I think I'm going to work with this here. And I'm going to do the torques around this point. I've got 2 unknowns here, so this is good. I'll pin it here. This wants to rotate it clockwise. This wants to rotate it counterclockwise. And watch how I'm going to get the torques around point C. I'm going to take n sub b. You could imagine moving it up along its line of action so that it's just this distance, or this distance, half the width of the ladder. That's 1 meter. So n sub b times 1 meter. That wants to rotate it this direction. I guess I've changed signs again, huh? It's rotating this way. The tension wants to go the other direction. Tension times moving it along its line of action times this vertical distance, which is half the height of the ladder. I did a little side thing here. The height of the ladder, I call it h. It's 4 meters up on the diagonal minus this side squared. You're just using the Pythagorean theorem, I can get h. And it'll be this tension, sliding it along its line of action, times that height is going to be the torque. So when you start to see how you can use this property, you can simplify this a great deal. And so we've got the torques, that's equal to 0. And so immediately I can get the tension in terms of the weight of the painter. Then once I have that, then you can go back to the sum of the forces in the x, and you can get F sub x. And some of the forces in the y, you can get F sub y. So you can take a problem that, again, would have had 5 equations, 5 unknowns, and do what you can before you take it apart if you have to get at internal forces. So there's a lot of things going on here. Dr. Young used this as a test question. It's a homework question. I think he even does it in class. But it has a lot packed in here, and you can see why he likes it. Okay, phew, good luck. Wow, I apologize. I know this is heavy-duty material. It's coming hard and fast, and it's not like you don't have anything else to do. Anyway, the very best of luck to you on your exam and also on your final. I'll stick around for a while if there's any questions.